All right, we're on. So, just to recap, we started with our I words, right? We had isotope. We know what an isotope is now. Everybody should be an isotope expert. Now we're going to talk about something called an ion. And with an ion, you're going to need your periodic tables in front of you because we're going to be using them. Let's move this out of the way. Okay? An ion is a charged particle. Okay, so we had this, where this was the atomic number. We had this, which is the mass number. And now we're going to have a new number that's going to go in the upper right-hand corner. We're running out of corners to put numbers in. It's true, right? We're running out of room. Okay. This right here is the charge on the particle. Sometimes it is called an oxidation number. Put that in parentheses, because sometimes you'll see it called an oxidation number. But I'm going to call it the charge. Okay? We know that if we have an atom, what is its charge? Neutral. Whoops. Yeah, oh shoot. Okay. An atom is neutral because the number of protons is equal to the number of electrons. Okay? Let's assume that we're going to take carbon. So my bottom left number here, my atomic number is going to be 6. We know if it's an atom, then it's going to have 6 electrons. Okay? Everybody's good with that? All right, take out your reference table. On your reference table, I'm going to blow this up real fast, and let's take reference tables for chem. I want you to take a look in the bottom left corner of this box right here where it says carbon, because it's big and we can see it. It says electron configuration. Kevin and Robert, pay attention to me. Okay? That's called the electron configuration. The electron configuration tells us where the electrons are and how many electrons are on each ring in the Bohr diagram. So let's look at a Bohr diagram. Okay? Let's say we're doing carbon. In the nucleus of a carbon atom, I'm going to make it red. This? That's all I drew so far. Okay. This is the nucleus of a carbon atom. In the nucleus of a carbon atom, I have 6 protons. That's what's making it a carbon atom. We also have, in the most abundant carbon atom in the universe, 6 neutrons. They're neutral. I'll stick them in there just to have them. We also know that there are these things called orbitals around the atom, which are also called energy levels. And we kind of talked about them way back when, right? They're energy levels. This first energy level right here is the n equals 1. It's the first energy level. It's the lowest energy level. That energy level, that n equals 1, can hold a maximum of 2 electrons. Okay? It can only fit. It's only big enough to hold 2 electrons. The n equals 2. Hold on. Let me write max electrons. Max electrons. I'm going to write it up here. Okay? So n equals 1. The max electrons is going to be 2. That's this ring right here. In the n equals 2, which is going to be right here, the max number of electrons that can fit in there is 8. In the n equals 3, now we're getting bigger, right? The max number of electrons I can fit in there is 18. That's n equals 3. I guess I shouldn't have put that arrow let's put the arrow here. Okay, that's n equals 3. And the n equals 4, the maximum number is going to be 32. Okay, I'm not going any higher than that. You don't need to know any higher than that. Make a little asterisk, a little star over here on the left-hand side of your little drawing that you made. And I want you to write the formula. There is a formula for calculating the maximum number of electrons that can go in each energy level. What?
There'd be another ring for n equals 4, right?
Oh, yeah, sorry. There's another ring here. I didn't draw it. Yep, good catch. Good catch. I'll just move that out a little bit. See if I can. How's that? Better? Okay, good catch. So, there is a formula that we use to calculate the maximum number of electrons that can fit in each energy level. And that formula looks like this. 2n to the power of 2. Where n is the number of the ring, the energy level. So if you, I'm going to go to the next page just so I have room. If you are in n equals 1, first energy level, first ring, it's going to be 2 times 1 squared. Now PEMDAS tells us we have to do parentheses, then exponent, then multiply, right? So we're going to do the exponent here. 1 squared is 1 times 2. Maximum number of electrons is 2. In the n equals 2, well, 2 equals 2 squared, because this number is the n in 2n squared. Okay? 2 squared is 4. 4 times 2 is 8. N equals 3. 2 times 3 squared, which is going to be 18. And n equals 4. 2 times 4 squared, which is going to be 32. Okay, that's where those numbers came from. Every once in a while, not very often, but every once in a while they'll ask you what the formula is to figure out how many electrons go in each energy level. Okay? Now, I went off on a little tangent here because let's go back to carbon. These numbers right here tell you how many electrons are in each energy level. Very convenient for us. Okay? So this first number right here is telling me that in the first energy level there are 2 electrons. So if I go back to my drawing, in the first energy level, which is this n equals 1, there are 2, 1 there, electrons. Okay? That's why I'm putting 2 electrons on that first ring. Easy peasy lemon squeezy. They tell you where they go. You don't have to remember where they go. Now, here's a big question of the day. An electron is negatively charged. Keep that in mind when I ask this question. Why did I put an electron up here and an electron down here? Isaiah? Opposites repel. They don't want to be anywhere near each other. So that's why I put one on the top and one on the bottom. Would you get it marked wrong if you put the 2 next to each other? No, you wouldn't. But get in the habit of putting them where they really belong. One on the top, one on the bottom. Okay? Now, in the n equals 2 ring, I can hold a maximum of 8 electrons. Let's go to carbon again. How many electrons are in carbon's second energy level? 4. Okay. So in this second ring, I need to put 4 electrons. And once again, they are negatively charged, so they want to be as far apart from one another as possible. When we diagram electrons, and they start to get a little bit more complicated, especially when you get up around 8 electrons and all that kind of stuff. This is how I want you to do it. Okay? Listen, everybody's eyes need to be up here because this is important. Okay? I'll draw them in green just so you don't get confused with the red dots. You're going to put your first one at the 12 o'clock position. 12 o'clock is up here. Then we're going to go clockwise. We're going to put our second one at the 3 o'clock position. Then we're going to put our third one at the 6 o'clock position and our fourth one at the 9 o'clock position. So it'll go 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. That's the AMs. If I needed to put 4 more electrons, which this one is not going to get 4 more because it's carbon, it only has 4. But let's say I needed to fill that up, then I would repeat 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Because in reality, there are electrons that are doing 2 things. One, if you have an atom, the electrons are spinning either in a clockwise direction or a counterclockwise direction, and it gets into all sorts of orbital stuff that I don't want to go into. But that's the way I want you to diagram them. I want you to go 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. You just drew your first Bohr diagram, okay, for carbon. You've got the protons in the middle. Sometimes you can write the neutrons in, and then we're going to write our electrons on the rings. Let me get another clean piece of paper. Let's draw another one. Let's draw fluorine this time. So let's do fluorine, and let's draw the Bohr diagram for fluorine. Let's put fluorine's nucleus in the middle. How many protons does it get? 9. 9 protons. Squeeze that little P plus in there. How many neutrons would it have when it's in the most abundant fluorine? 10. Excelente. Okay. Now I got to draw these rings. 1, 2. Okay, let's find fluorine. I want to show you something. Zoom into fluorine. How do I zoom in here? I'm just zooming in so we can see what's going on. Okay. How many rings does fluorine have? 2. How many electrons are going in the first ring? 2. 1 on top, 12 o'clock, 1 at the bottom, because they want to be as far apart from one another as possible for that first ring. The second ring gets how many electrons? 7. All right, I'll draw them in, I don't know, what color should we draw them in? Let's draw them in hot pink. Okay, it doesn't matter, I just want them to stand out. Where does my first one go? 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. That's only 4. I need 7. So what's going to happen is we're going to go rocking around the clock again. We're going to go again at 12 o'clock, again at 3 o'clock, again at 6 o'clock. Because in these pairs of electrons, one is spinning clockwise and one is spinning counterclockwise. Again, beyond the scope of this class, but that's why they pair up. They separate as far apart from one another as they can get until there's no more room. Then they will pair up with one going in one direction and one going in the other. Okay? So get used to how you're going to put them in. Okay? Is this second energy level full? No, it can fit one more. Okay? All right, everybody understand what's going on so far? Yeah. Okay, easy peasy lemon squeezy. Go ahead.
So wait, if there's more than 8, you triple them up?
Nope, there won't be more than 8. Okay? And I'll show you as we go along why there won't be more than 8. Okay? Let's take a look at this periodic table just so you can see something. Okay? There's a couple things happening here, and when we start talking about the periodic table in more detail, I'll repeat this again and again. But do you see how this line right here, which says 2, this horizontal row on the periodic table, that's called a period. And that second period, how many rings does it have? And if you look at the third period, how many rings does it have? And if you look at the fourth period, how many does it have? 4. You see this pattern that's starting to emerge? Mind blown, right? There's a lot of pattern on this periodic table. Okay? All right. I also want you to look at the columns. Look at all the elements in this first column. In the outermost ring, how many electrons do they have? 1. In the second column, how many electrons do they have in their outermost ring? 2. Let's skip over this 3 through 12 for a little while. Those have special names. Look at column 13, which used to be called 3A, but 13. How many electrons in their outermost ring? 3. 14, 4, 15, 5, 16, 6, 17, 7, 18, 8, except for helium. Why do you think helium doesn't have 8? It is special, all right. It is in the first period, and that means it's only got 1 ring. And that first ring, what's the maximum number of electrons that you can put in that first ring? 2. So helium can't have 8 because it doesn't have room to hold 8 electrons. It only can hold 2. Ooh, we're actually doing some real chemistry now. This is fun. I know you might not think it's fun. But look at the pattern that's emerging. It's so cool. Come on. It's cool. It is very cool. It does. It has its powers. Look at that. Okay? All right. Go ahead, Panak.
Iron has 14 more than
Okay. So, iron has 14 right here. And Panak saw it. Okay? In this section, from group 3 to group 12, those are called the transition metals. They are the inner, they are inside the periodic table. Periodic table is really these first 2 and those last 6. This section has what we call electron overlapping. So what happens, let's look at calcium for a second, okay? It's a pattern that's going to start emerging here. Okay, just hold on. Let me just draw the nucleus, and you know what a nucleus looks like. It's just a round circle. That's all I'm drawing so far. Okay? I know. Look how perfect that is. We've got 20 protons. Forget about the neutrons for now. In calcium, how many rings am I going to have? 4. Uno, doso, treso. What would a 4 be? Corso, catorso? That's really a word, though. I know, that's what I mean. That's 14. So I was trying to make up my own Spanish words. All right. So that's a crazy little diagram that I got going on here. I don't like it. Let me redo that. What's that? You're proud of me? I don't like it. 1, 2, 3, 4. Okay. There's 4 rings. And the reason that I'm using 4 rings is because calcium has 4 rings here. In the first ring, how many electrons am I going to put in there? 2. 1, 2. Now that ring is full, right? Okay, in the second ring, how many going to put in there? 8. 1, 2, 3, 4, 5, 6, 7, 8. In the third ring, I'm going to put in 8. 1, 2, 3, 4, 5, 6, 7, 8. In the fourth ring, I'm going to put in 2. What happened to it? Where'd it go? Okay. That's calcium.
Hey, wouldn't the 2 be like opposites?
If it makes you happy, sure. It's not going to matter. Okay, now, when we get to SC, I know you talked about iron, but look at SC. Look where the next electron is going to go. This was 2882. Where did the next electron go? What ring did it get added to? The third one. So instead of being added to the outside, it's being added to an inner ring. So with the transition metals, your electrons are not going to go onto the outside ring until they get all the way over to here. That is called electron overlapping. So the electrons, instead of being added to the outside, now get added to this ring.
We're on the tablet.
They start getting added to that third ring. And then if I went to titanium, it's going to go to the third ring. You see how it's going to 10? And then this one goes to 11. And then there's some funky stuff going on here with chromium. So it goes 13, 13. And that's because of the way the energy levels work. Don't worry about that. It's beyond this. Then 14, 15, 16, 17 essentially for copper, even though it says 18, and 18. And then what happens is, once that third energy level gets filled to 18, now my fourth energy level can get filled. Here, now you start seeing the fourth energy level go to 3, 4, 5, 6, 7, and 8. Okay? So this fourth energy level only puts 2 in. Then you got a bunch of electrons that start filing into the third energy level. And then finally, when you get to gallium, it starts adding to the fourth energy level again. And it has to do with how much energy those electrons have. Now, that's a lot. Okay, so there's some of you out there that's like, whoa, what the heck is going on? Here's the good news. On a Regents chemistry level, they give you the electron configuration. You never have to figure out where the electrons go. You're going to look right on here, and you're going to see, let's do zinc. In zinc, zoom in to zinc. Zoom. Okay. Come on, zinc. Okay. I have 2 electrons in my first, 8 electrons in my second, 18 in my third, and 2 in my fourth. You don't have to think about it. It tells you where they go. Go ahead.
Why is lead in the fifth period but only has 4 rings?
Lead. Where's lead?
PB. Or PB.
PB. Right here?
Oh, wait, no.
This is lead.
Wait, then what's PG? Oh, PG on the left side, sorry.
Here?
Yeah. Why does that have...
Because what happened was, it's more stable, and it all has to do with the stability of the atom. It's more stable to fill this fourth energy shell level than to have one electron hanging out by itself on the last shell. And so that's why it jumps down to a lower energy level. That's what happens there. I thought you were asking like down here. If you look at lead, why are there only 4 listed for lead?
Oh, same thing.
Well, because this little line, this little dash right here, is telling you that there's a 2-8 there, even though it's not written. And it tells you this right here down at the bottom of your periodic tables. Denotes the presence of 2-8 for elements 72 and above. So anything above 72, okay, has that little dash. That means there's a 2 and an 8, and then it goes 18, 32, 11, 2. Okay, that's what it's telling you. And again, this all has to do with energy levels. Where are the electrons going to be in their lowest possible energy levels? Electrons are kind of lazy. They want to be laying on the couch doing as little as possible. They don't want to go to work. They want to just be lazy. And so they're going to go in the lowest possible spot for the least amount of energy. And that is going to be in the lowest energy levels that they can find room for themselves. Okay? All right. Now, that kind of hints at Bohr diagrams. All right, hold on. Mr. Cherubis is calling me. Let's see. Let me turn it back on. So down here, all of these A are, most of them are man-made elements. They're going to just disappear very, very quickly. But also because, see how it goes from 57 to 72? Right. This is 58 to 71. These actually fit right in there. They have their own specific section of the periodic table. If you saw a periodic table like in all its glory, let me show you what it really would look like. Can you see on the thing? I want to show you one that's expanded. And they don't put it up here because it doesn't fit nicely on a piece of paper. Let's type expanded. That's really what it would look like. Okay, and it looks like this because these two rows, the lanthanide and actinide series, are usually put at the bottom of the periodic table because this would take an enormous piece of paper. So they said, all right, we don't use these guys that much. They're not very stable elements. Most of them are man-made. Let's take them out and let's put them at the bottom and just give people what they actually need, and that's this periodic table right here. Okay, so really most of the time we're going to be working up here. We will talk about uranium a little bit. We'll talk about plutonium a little bit when we get to nuclear chem. But for the most part, we're going to be up here. And even for the most part, we're going to be up at the very top. Okay? All right, so let's finish up this carbon. Actually, you know what? Remember that paper I gave you that looked like this? And I'll deal with the ions on Monday. You remember this? Do you still have it? It looked like this. You can't see anything? Remember this? We did it together? Okay, and I said, don't worry about this. We'll get to it. All right. Well, let's get to it. Why not? Let's take a photo. I'll do these. All right, let's look at the first example they gave us here, which is nitrogen. Does anybody need a copy? Okay, you guys are good. You all kept your thing. All right, nitrogen. I think that they wanted us to put, let's name it. So this is going to be nitrogen. You see it in the top left corner there? Okay. How many protons does it have? 7. Okay. That's its atomic number. We're putting the atomic number up here on the top. We're going to put the mass or the atomic mass or the mass number down here at the bottom. Again, we're going to go with the most abundant nitrogen. So what's its mass number? 14. Which means it's going to have 7 neutrons. You all following me? Does everybody know what's going on? Because if you don't, you have to say, hey, I don't know what's going on. Okay. How many electrons is it going to have? 7. Okay, let's draw the Bohr diagram. So when we look at nitrogen, it's got 2 rings. In the first ring, how many electrons are you going to put? And in the second ring, you're going to put 5. Golden. Okay, so let's pretend that this is my nucleus right here. In my first ring, I'm going to put 2 electrons. In the second ring, I'm going to put 5 electrons. 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. And then 12 o'clock. I think I wrote it in the wrong place. Yeah, 12 o'clock. Bohr diagram for nitrogen. Easy peasy lemon squeezy. Okay, let's do aluminum. Aluminium is 13 as atomic number. You see it? That means it's going to have 13 protons. Its atomic mass or mass number for our purposes is going to be 27, which means it's going to have 14 neutrons. How many electrons do you want to give it? 13. It's still an atom. Protons and electrons are equal. We didn't touch on ions yet. I was going there, but we didn't. Oh, I'm very popular today. Hold on. Okay, so back to this. My phone's making me very popular. Okay, so what is the order of the electrons that are being filled in for aluminum? We've got 2, 8, 3. So we come back over here. Here's my nucleus. I'll color it in. This time it's red. And I'll make my electrons blue. So 2. Then we have 8. 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. There's my 8. And then my last 3 are going to go 12 o'clock, 3 o'clock, 6 o'clock. Got it? It's not hard, is it? All right. Oh, didn't we do fluorine? Yeah, let's not do that again. Let's do argon. Okay? AR, argon. It's all the way over here. So we've got 18 as its atomic number. This is argon. And what's its mass? Let's do 40, right? 40. That means it's got 22 neutrons and 18 protons. It's going to have 18 electrons. And now let's fill them in. Here's my nucleus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Argon. Okay. Are we down to the last 5 minutes already? Yeah. Okay, I'm going to call it quits here. You can practice the last couple of these Bohr diagrams. When we come in on Monday, we're going to continue with these Bohr diagrams, and then I'll get into what an ion is, which is a charged particle, and how we're going to add and subtract electrons from these rings. Yippee! Yay, yippee skippy!